In this video, we're going to talk about the second derivative and what that is going to tell us about the original function. This one's going to be a little bit complicated, so try to pay attention, and then definitely make sure you ask me questions the next time you see me if you don't understand something. Before we get it to the notes, though, I want to review something that I call the fun chart. So here we're going to investigate the different connections between f, the original function, f prime, the first derivative. Remember, f prime, that's the same thing as the slope of f, the function above it. And now here we're going to get the second derivative, f double prime. And remember, the second derivative is just the slope of the first derivative, right? So these two things are the same, these two things are the same, and we're going to try to understand the connection between those three different functions. Let's do the first derivative first. If the first derivative is positive, right, if f prime is positive, that means the slope of f is positive, and that means f is increasing. Positive slope means going up, which means increasing. So first derivative positive means that your original function is increasing. Correspondingly, if your first derivative is negative, then the slope of f is negative, which means f is decreasing, right? And we call increasing and decreasing the behavior of the function. Behavior is just another word for slope, whether it's going up, whether it's going down, whether it's staying constant. All that lumped together is considered the behavior. So the first derivative being positive or negative, that sign chart stuff that we did in the previous video, that's going to tell us the behavior of the original function, and we can use that to identify maximums and minimums. Okay, now let's think about the second derivative, and this one's going to be tricky, so stay with me. If the second derivative is positive, that means the slope of f prime is positive. And if f prime has a positive slope, we could say f prime is increasing, right? So just like how the first derivative tells about the original function's slope, the second derivative tells about the first derivative's slope, right? So if f double prime is positive, that means the slope of f prime, the slope of the first derivative, is positive, which means f prime is increasing. Okay, now the next link. If f prime is increasing, that means the slopes of my original function are getting bigger. And if the slopes of your original function are getting bigger, it's going to create an upwards curvature to the graph, which we are going to call concave up, or concave upward. So if the second derivative is positive, that means the slope of f prime is positive, which means f prime is increasing. Okay, that's okay. But if f prime is increasing, that means the slope of my original function is getting bigger, and that slope of my original function getting bigger is going to cause an upwards curvature, concave up. So what you need to remember is the second derivative being positive means your original function is concave up like a cup. Now, if your second derivative is negative, that means the slope of f prime is negative, which means f prime is decreasing. And if f prime is decreasing, that means the slope of my original function is getting smaller. And if the slopes of my original function are getting smaller, it's going to have a downwards curvature to the graph. So that first derivative being positive or negative, that tells me the behavior, whether it's increasing or decreasing. The second derivative tells you the behavior of the first derivative. That's nice, but really what you want to know is, what does the second derivative correspondingly tell me about the original function? And the first derivative tells me what it's doing. Is it going up or is it going down? The second derivative tells me how it's doing that. Is it going up and curving up, or is it going up and curving down, right? It's going to tell you the shape or the concavity of your original function. So the first derivative tells you the behavior. We did that last time. And now what we're going to see today is the second derivative tells me the shape, concave up or concave down. All right, let's fill in the blanks and then we'll get to some examples. The graph of f is concave up if f prime is, if f is concave up, that means f prime is increasing. And remember, f prime increasing, that's the same thing as saying the slopes of my original function are getting bigger. And if the slopes are getting bigger, that graph is going to have an upwards curvature to it, which we call concave up. Next, the graph is concave down if f prime, let's go look, f is concave down if f prime is decreasing. Okay, so f prime increasing, that means concave up. F prime decreasing, that means the slopes of my original function are getting smaller. That means curving downwards. Original function is concave down. Now, we don't usually think about the first derivative being increasing or decreasing. Most of the time, we're just going to do the sign chart for that second derivative, figure out positive or negative. So here's the easier one, right? That first little table, that first little box, that's nice, but really this is the more, I think, simple one and the more logically straightforward one. If the second derivative is positive, then the graph of f is concave up. Concave up like a cup. And if the second derivative is negative, then the graph of the original function is concave down, like a frown. Okay, so that second derivative positive means concave up. Second derivative negative means concave down. Now, these are equivalent statements, right? F being concave up is the same thing as f prime increasing, which is the same thing as the second derivative being positive. Those are all equivalent statements. We just typically will use this and kind of just skip that middle step and go straight from the second derivative to the shape. Okay, now here, similar to when the original, or if the first derivative changes, right? If f prime changes from positive to negative, that means it was increasing to decreasing. That would be a max. Or if your first derivative changes from negative to positive, it means f is decreasing to increasing. That would be a min. So where the first derivative changes, we call those critical points. Those are either going to be mins, maxes, or sometimes neither. When the second derivative changes, those are going to end up being points of inflection, or inflection points. And those are when the graph changes concavity. It can change from concave up to concave down, or from concave down to concave up. So a function has an inflection point when the second derivative is equal to 0, or the second derivative is undefined, and the second derivative changes sign from negative to positive or positive to negative. Right? We need f changes concavity. That's the basic definition of a point of inflection, when the function changes concavity, which typically happens if you think about your sinusoid, right? Here you can see the graph was concave up like a cup. Oops, I'm not even on the screen. That's silly. You can see here the graph is concave up like a cup, but then there's some point where all of a sudden it switches and now it's concave down. This right here is what we consider a point of inflection, when the graph changes concavity. And again, that's going to happen kind of like how when we had critical points for the first derivative and those changed signs, it's going to happen whenever the second derivative changes. So we find those special values for the second derivative, the points that produce zeros or that produce undefineds, and we have to see if it's going to change negative to positive or positive to negative. But the second derivative changing sign is the same thing as your first derivative changing slope. It could be decreasing to increasing or increasing to decreasing. Again, I wouldn't really worry a whole lot about this. Like this, the top layer is the one that we really concern ourselves more with. The second derivative changing sign is going to tell us the concavity, in which we can use to find the points of inflection. Then here's a nice little note. It's all capitalized, probably because students miss points with it all over the time. It is not enough to say there's an inflection point. Just because the second derivative is 0, there also has to be a change in concavity. So the second derivative being 0 means it could be a point of inflection. Just like how the first derivative being 0 means it could be a min or a max, but you still had to do something to determine how it changed and if it changed. Kind of similar for the second derivative, you need to make sure that it does change, either from plus to minus or minus to plus. The order doesn't matter, but you need the concavity to change. Okay, now let's go back and kind of revisit something that we did in a previous notes packet. We talked about things like increasing at an increasing rate or increasing at a decreasing rate. Right? We've seen these 4 basic curves before, but now that we have the first and the second derivative, now we know increasing and decreasing. Now I can use a little bit better labeling system for it. Right? So let's see, the shape number 1 has a basic graph like this. It's definitely decreasing, so the first derivative would be negative. But then as you can see, like this graph, both for shape 1 and 2, that graph is shaping and it's curving downwards, concave down like a frown. And you can also think, are the slopes getting bigger or are the slopes getting smaller? Here it's like a negative 1/10. Maybe it's like a negative 1, then maybe like a negative 5, then maybe a negative 10. The slopes are getting more negative, which means smaller. So here it's going down and the slopes are getting smaller. The slopes getting smaller creates that concave downwards curvature. So this would be your negative case. It's decreasing at a decreasing rate. The slopes are getting smaller, concave down. Okay, let's go shift it over to 2. Here the function is increasing. It's going up, so the first derivative is positive. But here it starts off with a big positive slope, like a 7, and then it's like a 4, and then it's like a 1. So the slopes are always positive because the graph is increasing, but the slopes themselves are getting smaller. So that's your increasing at a decreasing rate. It's going up, but the amount that it goes up is getting less and less and less each time. So it's going up, but it's concave down. There's your shape 2. This is decreasing, certainly, so your first derivative is negative. And then let's see, what are the slopes doing? It looks like a negative, a pretty big negative, then it's less negative, then it's less negative, then it's less negative. Slopes are always negative, duh, but they're getting less negative. And if something is getting less negative, that means it's getting bigger. And you can see the shapes 3 and 4, those both form your concave up like a cup shape. So that's your decreasing at an increasing rate. It's going down, but it's curving up. And then here's the easiest, the plus. It's increasing at an increasing rate. It's going up and it's curving up. It's increasing and it's concave up. So every graph that you have ever done or will ever do breaks down into little pieces, and each piece is either a straight line or it's one of these 4 shapes based on the combination of your first and your second derivative and what plus, minus, minus, plus, or minus, minus case you may have for that specific interval. Okay, so the fun chart up there at the top, definitely you want to know this. Copy this down in your notes. Make sure you understand it. If you don't understand it, just straight up memorize it. That's okay. That's important though. Make sure it gets in your brain. And then these 4 basic shapes, that's going to help us when we do our curve sketching here on the next page. Okay. Again, concavity, it doesn't matter. It can change from up to down, or it can change from down to up. How it changes concavity doesn't matter. It just has to change. If it's concave up to concave up, that would not be a point of inflection. Or if it's concave down on both sides, that would not, right? It's got to change concavity in order to be a point of inflection, aka an inflection point. Okay, last example on this page, we're just going to see whether the first derivative is a plus or minus, whether the second derivative is a plus or minus, and then we'll be done with this example. Then we get to do the next page. Definitely looks like this function is decreasing, right? If you were to think about any specific tangent line, all of those tangent lines have negative slopes. So here your first derivative is less than 0 because f is decreasing. Okay, so we got that one. There's a minus. And then we're going to see, okay, is it concave up or is it concave down? Try to trace it. Are the slopes getting bigger or are the slopes getting smaller? It starts off with a fairly negative slope, and it stays negative, but it's getting flatter. So the graph is getting less negative. And if something's negative, but getting less negative, that means getting bigger. And you can kind of see the concave up curvature too. So the second derivative is going to be positive because f is concave up. The slopes of f are getting bigger. Creates that upwards curvature, concave up. Okay, so the first derivative tells me the behavior, increasing and decreasing, which we use to find max and mins. The second derivative tells me the shape, which we use to find points of inflection. Let's do this example, which is a pretty typical calculus question. It's pretty long, not terribly hard though, once you know all the conceptual stuff that's going on behind the scenes. And this is like your numbers 1 through 4 on your homework. Parts A and B is what we could do with just the first derivative stuff, but now we know concave up and concave down. The second derivative sign chart is how we're going to answer C and D. All right, so F prime, that sign chart is how we do A and B. And then the second derivative sign chart is how we do C and D. Let us go for it. The first derivative here be 4x cubed minus 12x squared. Let's factor. 4x squared can factor out. And then an x minus 3. So there's your first derivative. That's never going to be undefined, so we just got to find the critical points where it's equal to 0. And there are 2 of them. So that's great. Let's go take this information and let's go do a first derivative sign chart with it. The critical points that I need to test, 0 and 3. And then we're going to see, hey, when is that first derivative positive? When is it negative? That'll give us everything we need for A and B. All right, so let's plug it in. That left chunk, it's 4x squared. I know that left chunk is just always going to be positive, so that's great, right? Anytime you have something squared, just plug in, that chunk is always positive. So now all I need to do is worry about the x minus 3. If you pick a number like 4, that chunk would be positive, which means overall positive, which means your original function would be increasing. If you test a number like 1 for this middle interval, 1 minus 3 would be negative, which means overall it's going to be negative, which means f would be decreasing. And if you pick something like negative 5, that chunk is negative, overall negative, so decreasing. Okay, so let's think. Is 0, which is a critical point, is that going to be a min, a max, or neither? Well, it's negative for the first derivative on both sides. That means it's decreasing, flat, and then decreasing again. So that would be neither a max nor a minimum. But 3, the derivative changed from minus to plus, which means your original function was going down, decreasing, then it goes up. So we know that point has to be a minimum. Okay, so let's go through and let's answer some questions. F is increasing when your first derivative is positive. Therefore, 3 to infinity. F is decreasing when f prime is negative. Negative infinity is 0. Union 0 to 3. If you were to just say negative infinity to 3, that's okay. I would suggest you throw out the value of 0, but you can lump those together if you want. Okay, let's see. F has relative min at x equals 3 and no relative max. And again, that's all by first derivative test. So we've got all the answers for A and B. Now we're going to do that same process, but instead of using the first derivative and its sign chart, we're going to use the second derivative and a new sign chart. And that second derivative sign chart is going to answer C and D. So let's go find this second derivative and do this process all over again. Here we've got a 12x squared minus 24x, which is going to factor. So I've got x equals 0 and x equals 2. Those are your special values for your second derivative. Let's go take that second derivative sign chart and figure out when it's plus and when it's negative. Okay. And again, we're plugging it in right here, right? So 12x and then the x minus 2. If I plug in a number like 5, that would be a positive. 5 minus 2, that would be a positive. So then overall, it's going to be a positive. And that second derivative tells you the concavity. So your original function is going to be concave up. Test a number like 1 for the middle interval. That's going to be a positive. 1 minus 2, though, now that's negative. So overall, you'd have a negative, which means concave down. And then for the last interval, something like negative 10, that chunk would all be negative. That chunk would be negative. But those two negatives would cancel. So positive and then concave up. Okay, so we did the second derivative sign chart, but instead of increasing and decreasing, it tells us concave up or concave down. Okay, so let's see. F is concave up when the second derivative is positive. So that was from negative infinity to 0. And then from 2 to infinity, F is concave. Oh, I'm kind of off the screen, aren't I? Sorry. F is concave down when the second derivative is negative, which was between the 0 and the 2. So there's your answer for part C. And then we need the last one. Is 0 going to be a point of inflection? Does it change concavity? Well, on the left side, it was concave up. On the right side, it was concave down. So yes, that is a point of inflection because F changes concavity. And then at x equals 2, it was concave down on the left. Then it changes to concave up. So yes, since the graph changes concavity at that point, it will be a point of inflection. So we'll say F has point of inflection at x equals 0 and 2 because F changes concavity. And you could say second derivative changes sign. That's an equally good justification. But if you just say F changes concavity, your justification is always going to be good. You don't have to worry about writing anything else. But there are other equivalent statements you could say, like second derivative changes sign. But I would just recommend F changes concavity. So we've done increasing. We did decreasing. We did the extrema. That was all from your first derivative sign chart. We did concave up. We did concave down, and we did points of inflection. That was all for my second derivative sign chart. Now the last thing is to try to sketch the curve of this graph. So what we need to do is break this graph into little subintervals and figure out what's the combination between your first derivative and your second derivative. And then that'll tell us which one of the shapes. Remember here, I'm going to just draw the shapes again. You have the 4 basic shapes. 1, 2, 3, 4. And then this graph is going to break into little pieces, and each one of the pieces will be one of those 4 shapes. Okay, so let's think. Anytime either of these two, I need to zoom it out, don't I? Anytime either of the two derivatives, either the first derivative or the second derivative, anytime either of the two functions changes, we need to break it up and have a new interval. So here my first interval, negative infinity, and then let's see, the first time either of them changes is at 0. So from negative infinity to 0, I need to figure out what my combination is. And it looks like everything to the left of 0, the first derivative was negative, second derivative was positive. So that's your decreasing at an increasing rate. So you're thinking about it has to be a shape like this. It's going down, but it's concave up. It's going down, but it's curving upwards. First derivative was negative. Second derivative was positive. Okay, now let's think about the next little interval. They're both states. That one's still negative until 3, where it changes. But then this one's negative until 2. So the next interval is just 0 to 2. And between 0 and 2, the first derivative is negative. But between 0 and 2, the second derivative is negative. So that's your decreasing at a decreasing rate. It's decreasing and it's concave down. So then that would be a shape like 1. And then the next interval, it's going to be from 2, and then something changes at 3. So from 2 to 3. And then let's see, between 2 and 3, that first derivative is still negative. Okay, it wasn't positive until after 3, so we're getting there. The first derivative is still negative, but now the second derivative between 2 and 3, second derivative is positive. So there's another decreasing at an increasing rate. So it's going down, but it's concave up like shape 3. And then the last interval is just everything after 3, right? Nothing changes in the second derivative, nothing changes in the first derivative once you're past the x value of 3. So let's see, the first derivative is a positive. The second derivative is still positive, so that's your plus plus. That's your shape for increasing at an increasing rate. So now I know basically what this graph is going to look like. I don't have any points of reference though. So let's start. Like if x equals 0, let's go back and plug in and find the y-intercept for this graph. If I plug in 0, you're going to get out 0. So I've got an initial coordinate point. You've got to know somewhere to start. And I could find more coordinate points, but we're just going to sketch. And so it doesn't have to be super precise. Right, and really even the y values, they don't matter. So let's think. 0 to 2. All right, they're your intervals. Negative infinity to 0. We know the graph has to have a shape like this. Then between 0 and 2, it's going to have a shape like that. Then between 2 and 3. And then everything to the right of 3. Oh, you definitely can't really even see the little dashed lines that I did. Sorry. Okay, let me zoom it in. So everywhere to the left of 0, we need the graph to have a shape like this. And I know this coordinate point, and so I'm just going to kind of work my way backwards. So there we go. That's what the left side could look like. Don't worry, the arrow is pointing to left. Remember, you always read from left to right. You just put that arrow on the left because it continues in that direction. But the shape, as you move from left to right, needs to be decreasing but concave up. Right? That's what we just found. Now between 0 and 2, you need a shape like this. I don't know how far it's going to go. Like maybe you do something shallow, or maybe it's a little bit steeper. We don't really know for sure, right? If you wanted to be a little bit more precise, you could always plug in 2 and figure out exactly where that y coordinate's going to be. But we're just sketching, so it doesn't have to be super precise. So I'm just going to do a little shape like that. I'm going to say it ends right there. Again, the y value doesn't matter. We're sketching. Then between 2 and 3, we need the graph to have another shape like this. And then everywhere to the right of 3, it needs to go up and increase. So there we could have gotten, right, we got a fairly decent sketch of this function. It's not like super accurate, right? Because I don't know exactly where all these y coordinates are. If you plug them into the original function, you could figure out exactly where they are. But we're really just caring mostly about the shape, right? And this graph breaks down into little pieces, and each one of those pieces is one of those 4 curves, just based on the combination of your first and your second derivative. And every graph that you have ever done or will ever do breaks down similarly. Excluding lines, right? Lines have 0 concavity. If you take a second derivative of a linear function, it's going to be 0, so they have 0 concavity. But any other curve, any other function, just breaks down into pieces, and then all of those pieces are just determined by your first and your second derivative. So kind of nice, a little bit weird, very conceptual. Hopefully it makes sense. Okay, moving on to the next example. We've got to sketch a graph given all of these specific characteristics, giving all of these criteria. So let's read them. Let's try to figure out what graph it could potentially look like. And then we'll be done with this video. First thing, f of 0 equals f of 2, which equals 0. That's just telling you you have x-intercepts at 0 and then at 2. That one's not too bad. Then it says f prime is positive for everything less than 1. So that means your graph f is going to be increasing. Then it says the derivative at 1 is 0. So that means it's going to be constant. Then the derivative is negative. So it's going to be decreasing. So I know it's like increasing. Then it's decreasing. And right at this point, it's constant. And then it says the second derivative is always less than 0. So your function is always concave down. So let's think about the combinations. We've got, I think, 0, everything to the, oops, not negative 1. We've got everything to the left of 1, and then I've got everything to the right of 1. And let's try to figure out what shape would go in to both of those regions. To the left of 1, it's got to be increasing. but it's concave down. So it says the first derivative was positive, but the second derivative was negative. So if you go back up to your four shapes, positive and concave down, looks like it's going to be a shape like this, the shape 2. Okay, and then the next interval, it says now the first derivative is negative, and the second derivative is still negative. So that's your negative, negative case. That's the one that's going to look like this. So I know I've got to go through this point. You don't really know what the point is going to be, right? What the height is when x equals 1. But I know the function is going to have a shape more or less like this. Again, I don't really know exactly what that y value is, but it doesn't matter. The graph is going to look something like this, that shape to the left of 1, and then it's going to look something like this to the right of 1. And then that would be a fairly decent sketch. Could be like a parabola that opens downwards, a negative quadratic. And if you were to check all of these conditions, they are all going to work for that type of a graph. All right, so we're good. Let's move on to the last one. Here it's similar. You've got the x-intercepts in the same spot. You've got increasing. You've got an undefined derivative, which could mean something like a cusp, or it could be something like a vertical tangent, or it could be a sharp turn. It can't be a discontinuity because the instructions actually say it's continuous, right? So it can't be a discontinuity. It can't be an asymptote, can't be a hole, can't be a jump. It's got to be a continuous function. So it's got to be one of those other 3 issues that could cause your derivative to be undefined. Then it's going to be negative, and here it's concave up on both sides. So let's think about the combinations and then what the shape would be for each one. Here, if it's positive, you know the graph is going to look like this. And then it's going to be negative, positive for that other interval. So it's decreasing and concave up, which means it's going to look like this. So we have a graph that starts off and does something like this. And then I need to switch it. And then it has something like this. Now, those 2 points got to be connected. It's not a vertical asymptote, right? It can't go up and it can't go up. It can't be an asymptote because it's got to be continuous. That one actually is not differentiable because you have the cusp right there at x equals 1. But that would be a fairly decent sketch for your original function. Again, what that y-coordinate is, we don't know for sure, but that's okay. We're just sketching. It doesn't have to be super precise. But there's a pretty decent sketch given what all those characteristics and criterion were.